I am very pleased to introduce Adam Gazzaley, who is a dear friend of mine. Adam is, I think, well on his way to being one of the great neurologists of our time. He's been on the cover of Nature magazine for some of his neurogaming activities. And anyway, he'll tell you all about it. He's going to literally blow your mind. Adam Gazzaley, come to the ARC stage.
Hello, everyone. Welcome. Thanks for having me here. It's exciting to present right next to my lab. I work at Mission Bay campus at UCSF, so just a 5-minute quick ride away. I have a very short time with you. This is really not a conference. It's just an event and a party. So I'm going to just give you essentially a teaser, like a little appetizer of what we do in my lab. This is the topic I'm going to talk about, really bridging tech and neuroscience. It's become a big interest of ours. I would say if I had to break it down and distill it to one goal that we have, it's developing approaches that are effective with low side effects to enhance cognitive abilities in both people that are healthy and those that are impaired. So how do we do that? So we are trying to come up with innovative approaches in our lab that do not use the classical route of molecules and essentially drugs to improve how the brain functions. Not that those ways are not effective, but there's high side effects and there's lack of selectivity. So that's some of why we have deficits, at least on the medicine side. So what we're trying to do essentially is build an engine of change, to change the brain in a way that's meaningful and sustainable over time. So if you're going to build an engine, the first thing you need for that engine is fuel so that it runs. This is our fuel for everything that we do in our lab. We harness this natural fuel of our brain to change itself, known as brain plasticity or neuroplasticity. It's our brain's ability to modify itself at every single level, from function, physiology, to structure, anatomy, to chemistry, in response to challenges and new experiences in the environment. There was a period of time that we thought that this really ended after critical stages of development, and then you just decayed your entire life. We know that's not true, that this ability to modify your brain exists throughout our lives. So we just want to find an engine to harness this. One of the engines that we build, and probably the main one in our lab right now, is video games. The average age of gamers are approaching 40. It's almost completely gender balanced now. It's global, and it's a multi-billion-dollar industry. So from every perspective, it's a force. What we want to do is harness this and show that it can have positive impact. Around 5 years ago, I reached out to friends of mine that worked for George Lucas's video game company, LucasArts, when it existed there in the Presidio, and asked if they would come down to my lab and help build a video game that I came up with to challenge the cognitive abilities of older adults. So we had already spent many years using techniques like functional MRI and EEG and transcranial brain stimulation in our lab to understand the vulnerabilities in the older brain. And one thing we realized that attention abilities, working memory, goal management, these are known as cognitive control abilities that allow you to interact with a complex environment in a really dynamic way. This declines when we get older. So this game was designed to challenge the brain of older adults in this very adaptive way to put pressure on these processes and lead to improvement. This is a look at what NeuroRacer looked like. It's a car driving game. You have a joystick. You're trying to maintain the car on the road. It's moving all over the place, demands a lot of attention. These signs come up. You have to press the button as rapidly and accurately only to target signs like the green circles, not red circles, not green pentagons, which is actually very hard not to press it for. And so we built this game, and then we wanted to see, can we use a video game as a diagnostic and as a therapeutic? So what we did first was we used the game to see how people's abilities to multitask, which we know gets worse when you're much older, how it changes across the lifespan. So we brought in a whole bunch of participants across the age span and had them play the game. What the red line here means, at 0%, it means that you do that sign task equally well when you do it alone compared to when you're driving at the same time. And if you ask a 20-year-old how they would do on that, they said that they will have a 0% because they firmly believe that they are multitasking masters. If you look, what we see is that they drop 27% when they do these two tasks simultaneously. We already know that 70-year-olds are going to have trouble with this because we've been publishing papers on that for a decade. But what happens in between? Do you just hold this ability at this high level and just plateau in one horrible year when you're 69? That's not what occurs. You plunge every single year. So we really see that getting older is not about being in your 60s or 70s, it's about being not 23 years old anymore. So these skills decline throughout our lives, and we could see that we could use this game as a really sensitive diagnostic, even seeing significant differences between 20-year-olds and 30-year-olds. We can also use this as a neurodiagnostic. So if we record brain activity using a 64-channel EEG cap, as you see in this picture, we can see the frontal cortex, the most evolved part of the brain, responding rapidly and dynamically at the most challenging part of the game, when a sign comes up and you're also driving. So right there, within a third of a second, you get a blast of activity in this frequency range right from the front part of your brain. So that what we do is we bring back another group of older adults, and we distribute laptops in a collaboration with Apple at the time around the Bay Area, and we have them play. We have other control groups. But essentially what we're interested in is how their performance on this game changes a month later, what changes in their brain, and what changes in terms of their other cognitive abilities. So the first piece of data is that their ability to multitask exceeds that of 20-year-olds, even after just a month of practicing in this game environment. So this is very exciting. We start learning how we build games that lead to improvements that then leave those games. And we could see that the change in the brain activity in those that it was strongest actually showed the biggest improvement in this other task, the attention span task, and actually showed sustained improvement 6 months later, even though they didn't continue to play the game. We're very excited, and what you see here is the title of the journal. They say Game Changer. That's, while it's very thrilling to see such a title, it actually was quite intimidating, and it took a lot of sort of messaging to redirect what we think the game changer is. So any game changer, I hope it's that methodology that then you could carry over and build essentially a new class of diagnostics and therapeutics around technology. Just a quick glimpse of what's happening now. We have the strong desire to move it beyond the lab into the real world. And so I helped co-found a company called Achille Interactive Labs. I keep my day job. I just serve as an advisor. And what Achille is doing is building a way better game, better science, better art, music, story, more accessible on the iPad. And now going through the steps of validating this in a full-out FDA approval pathway and seeing if you can get a game prescribable. So I'm a neurologist myself. Would a neurologist pull out a prescription pad, or a psychiatrist write a prescription of a game? Can it be reimbursed? At that level, are we talking about at least an adjunct to our current pharmaceutical pathway, which is incredibly siloed right now? So all of these studies are ongoing. I don't know the answer to any of these questions if this will work. I think there's a lot of strong hypotheses of why this game would work in these populations, but we'll know that over the next year or two. In the meanwhile, we kept coming up with new ideas, and we realized that we didn't really have a lab to do the type of studies that we wanted to perform. So we just built a new lab at UCSF at the Mission Bay campus right down the road to really bridge this gap between technology and neuroscience. And this is a quick snapshot of what our building looks like. If you haven't been over there, it's really quite a beautiful place. And this is our new lab. Some of the folks are sitting right here. So what we essentially built was what would be thought of as like a high-tech media lab, but put it right inside a neurology, psychiatry, and neuroscience center to really bridge those worlds. So we could present these dense, beautiful, interactive environments, carefully controlled, and then record a ton of data, from eye movements to body movements to brain activity to autonomic responses, to, to all sorts of ways of measuring how someone's interacting in this game at that moment. Some things we're really excited about. Mobile, we see great potential to reach places in the world where you don't get medicine frequently. We're also excited about mobile and wireless, not just in terms of tablets and our game can be played on them, but in terms of recording data. So we're working with many companies now to develop high resolution, high fidelity, and robust EEG caps. So we want to do the first experiment ever where we have people play our games at home wearing an EEG cap, and we can capture their brain data remotely to look at the path of plasticity over time. So that's something we're excited about. One of our games, called Body Brain Trainer, is one we're all very excited about. Some of our development team is here. The idea is that we could have an integrated platform to push you both physically and cognitively at the same time, using the same type of adaptive approach with feedback loops. Here's a quick picture of what it looks like in our lab. We find that the physical and the cognitive elements can be used to play off of each other and enhance each other as opposed to compete with each other. And then the goal is to say, if you play this version of the game that's both physical and cognitive, will your cognitive benefits be better than if you played that same game with a joystick? Does the embodiment of the physical fitness of it lead to a quicker learning curve? We have all these experiments that will be starting in 2015. Right now, they're development projects. Meditation game, rhythm, attention, physical and cognitive fitness. They'll all be separate experiments, but the real mission is to unite them and to think about how we can push on plasticity in a very multimodal approach, sort of a neuro CrossFit training program where you push on all of these different aspects of how your brain functions. I'm excited to actually participate in all these. For the first time, I actually challenged my lab, most of which are 20 years younger than me, that I could compete against them on all of these games. So we're going to all start this in 2015, see what we could do to our own brains, and hopefully become like a neuro Ironman. So that's the goal. We gave you, hopefully, a nice preview of how we're pushing game development, both as a therapeutic, a diagnostic, new games. We think that we could go further using other technology like mobile EEG, neurofeedback, brain stimulation. So I'm going to show you about a very early, if we have like an X lab, this is what it would be, developing something that's probably not even going to appear until 5 years from now. So all of our video games work on adaptive loops, right? So we present the game, people play the game. The game is challenging them because it's learning how they're performing in real time. What if we can see what's happening inside your brain in real time and use that information to guide the gameplay? So what we're going to show you now is a prototype that we've been developing for a couple years. We call it the glass brain. It's still very early prototype, but I think it'll give you an idea of where we hope to go in the future as we continue our game development work. So we get an MRI scan so we can see all the detailed structure of the brain, and we actually use the MRI scan to inform the EEG data, and that's why we need so many electrodes, to localize in the brain as precisely as possible where those signals are coming from. So this is a skin on top of the brain. There's another thing going on here. Rajat is wearing an Oculus Rift, actually the latest model, and could you look around a little bit? So you're seeing two, but he's seeing one 3D immersive, very real view, a virtual reality view. So these just represent what's going on in each of his eyes. There's two different types of MRI images that are overlaid on each other, a structural image. So what we could then do is take EEG data, and like I said, in real time with just a 100 millisecond delay, correct the artifacts from it, source localize it using the MRI data, and display different frequencies with different colors. So the different colors represent different frequencies. So basically what you're seeing now, Raj over there has a joystick. So this is not a video. It's essentially taking this data, it's quite beautiful I think, both the MRI data and the EEG data, we bring it into the game engine that we use for all our development known as the Unity game engine, and then you could essentially just fly through the brain functioning in real time. It's still very early, but it's something that we're all very excited about in the lab. But what we're most excited about is having this game not just adapt to the performance, but adapt to the signals that are being captured, so that the game can essentially diagnose what's strong or weak about how your brain processes information in real time and use that to guide the rewards and the adaptive cycles of the game. So the game becomes essentially like a gamma knife, right? Putting pressure on those processes of your brain that need to be optimized. And we think that this will have great potential. So we think that these closed loops between the video gameplay, the neurofeedback of the game adjusting to what's going on in your brain, and even potentially stimulating your brain, also in a closed loop using that neural data, will be a very powerful way to rewire circuits to lead to better performance. And we're not talking about this as a cure of certain diseases, like Alzheimer's, but a way of strengthening the brain so that if you do have an invading army, you have a better ability to resist that. So that's it. Thank you, everyone.
Thank you, Adam. Do you mind taking a couple questions? Anybody have any? Bruce?
So that is absolutely brilliant. I just saw the future. Intuitively, I think everybody in the room could say, yeah, I get it, but why do games work on brains? Does it go back to live or die in caveman era? Why does it work?
Yeah, that's great. The basic idea is that all of our drugs fail us right now. I hope that's not true forever, is that they are non-selective. They act like a sledgehammer. They act maybe for a neurotransmitter system, but not on the circuits, these beautiful networks in the brain. And so therefore, doses have to be raised very high to get effects, and then you wind up with side effects. And most of what we do as physicians is really manage the side effects. The power of the video games is that because of the very nature of how your brain works, they activate circuits in a very selective way. I mean, we essentially use games in all of our cognitive neuroscience research. It's just not very fun. We don't call them games, we call them paradigms. But when you interact with something in the world in a very specific way, your brain reacts selectively. It's the only way we really know to selectively activate entire networks. So interactions with the world activate networks. So games do that naturally.
But by the way, this is really fusion at work. I mean, not only do we have bioscience, all the data you're working on, trying to keep people healthy, even reverse aging in the brain, or make you younger, but also the arts aspect. So Adam, I mean, I don't know about you guys, being up on the stage here, I almost feel seasick with all of these images back here. This is really stunning. And we would love to have you all continue in the journey that we're launching tonight with ARC. And thank you so much for coming tonight.